Okay, so this is a substitute fill-in class for Wednesday's class that you got off, and I will see you on Friday with your homework. Bring your homework on Friday. So let's talk about logarithms. Let's start with an exponential function example to kind of motivate this. So we have a bacteria population starting with 630 bacteria, growing 45% every day. This is review. We're going to determine the one-day growth factor, the function that outputs the population, x days after there were 630 bacteria, and the number of bacteria at 10 days. So all should be very familiar and good at answering these questions. What is the one-day growth factor? You should have said 1.45. What's our function? Our starting value is 630. Our growth factor is 1.45. So we got the function 630 times 1.45 to the x. And how do we find what the population is at 10 days? Okay, well, we're going to plug in 10 for x into our function and crank out the function value, which will give the population. Now, when you see this expression, let's see here, if I can get this going. When you see this expression here, 630 times 1.45 to the 10th, you should always keep in mind the image of what's going on here, and don't get into the habit of just forgetting that, plugging in 10 and cranking out the answer. So let's review what is that image that you should have. Well, 630 is the number of bacteria at day 0. And what happens? What is going on with this 1.45 to the 10th? Well, on day 1, we'd have 1.45 times 630, because that's what the one-day growth factor is. It gives you the amount one day later. Okay, so then on day 2, we'd have the amount on day 1 times another 1.45. So continuing this way, once we got to the 10th factor of 1.45, that whole product then would be the number of bacteria on day 10. And we know that we can write 1.45 multiplied together 10 times as 1.45 to the 10th. So that's where this comes from. And when you see something like that, what I just explained through here should be your image of that. Don't forget the basics. When you get into trouble on a difficult exponential problem, this idea that I just explained can get you out if you understand it. Okay, so here's the situation, here's our function. So here's a new question. How many days will it take for the population to grow to 500,000 bacteria? Well, this is different, because the known 500,000, that's actually our output. And what's unknown, how many days, is the input. So let's walk this out. We'll put in 500,000 for the output. Our first step in solving for x would be to divide both sides by 630. And then we can simplify that, and we get this expression, 793.65 equals 1.45 to the x. But the question is, what now? How do we solve for x? We don't really have an algebraic thing we can do to say x equals. But we know there is some value, so that some number of days that will get us 500,000 bacteria. So we can start by just saying that x is the exponent of 1.45 that gives 793.65. But we want a mathematical, kind of a compact way of writing out that phrase. So as an idea, the value of x, this is exactly what it is. It's the exponent of 1.45 that gives 793.65. But we want to, like I said, we want a compact mathematical way to do that. And so the notation that we have is called log. Okay, so the purpose of a log is to be able to solve for an exponent. Okay, this exponent of 1.45 that gives 793.65, our notation is the log base 1.45 of 793.65. So in other words, logs are exponents. This log right here is this exponent, x. What is it? It's the exponent of 1.45 that gives 793.65. So that particular exponent turns out to have the value 17.97 days. Okay, we'll explain how to actually get that value later. Okay? We haven't really said that yet. But first we need to practice this new idea of log. So again, logs are exponents. This was the statement we had on the last page, that 1.45 to the x equals 793.65. And we said that's equivalent to x equals the log base 1.45 of 793.65. Both these are saying the exact same thing. Both these statements have the same meaning, and that meaning is that x is the exponent of 1.45 that gives 793.65. So let's show how both of these statements mean that very thing. So here we see x is the exponent of 1.45 that gives or equals 793.65. Similarly, x is, or x equals, that log right there, log base 1.45 of 793.65, that's exactly what that is. It's the exponent of 1.45 that gives 793.65. And like I said, that's the log base 1.45 of 793.65. So let's look at some more examples. And so you can practice. You can stop the video and practice on each one. So we're going to describe in words exactly which exponent it is, and then you're going to write your description as a mathematical statement, which will actually allow you to solve for what that log is. So here we go. So the log base 5 of 25. So exactly what exponent is that? So this would be a good time to pause and verbalize. This is what I'm after right here. Verbalize like this what the log base 5 of 25 is. The log base 5 of 25 is the exponent of 5 that gives 25. That's what this means right here. This is the exponent of 5 that would give 25. So mathematically, this is how we set it up. A is the exponent of 5 that would give 25. And we know what that is. That's 2. So since A is 2, that's what the log base 5 of 25 is, because this is saying the exponent of 5 that would give 25, and that equals 2. Okay, another practice problem. Okay, here's another example. So we want to kind of flesh out here, what is the log base 2 of 16? I'm calling it z, but the focus here is what's the log base 2 of 16? So pause the video and describe in words exactly what it is, and then write out a mathematical statement that matches your description. Okay, if you did that, you should have had that we're talking about the exponent of 2 that gives 16. So that statement would be that 2 to the z is 16. The exponent of 2 that gives 16. And that is 4. And so since z is 4, the log base 2 of 16, or the exponent of 2 that gives 16, is 4. Another example. Okay? You're going to describe in words exactly what the exponent means, and then from that description, write it out as a mathematical statement. Pause here. Okay? You should have gotten that. We're talking about the exponent of 4 that would result in or give 1 over 64. So if we call that exponent p, then we want 4 to the p is 1/64. So here I've changed that to 1 over 4 cubed. So what's the value of p that would give 1 over 4 cubed? That would be -3. So the log base 4 of 1/64 is, again, the exponent of 4 that would give 1/64. That exponent is -3. Remember, logs are exponents. So let's take a look. So here's some more examples that you should practice with. These are number 2, problem number 2 in worksheet 8 and module 4. You could open up your book and you could, again, do what we're talking about. So for each log, describe what it is in a sentence, and then rewrite, based on that sentence, write it as an equivalent mathematical statement. And then for the ones that you can solve just by looking at it, knowing what that exponent is, go ahead and do that. So pause here and work on all these items. So I want to point out a couple special ones here. So let's look at g. So g was the log base 10 So let's look at g. G was the log base 10 of 10,000. So we could describe that as the exponent of 10 that would give 10,000. Or 10 to the, they called it g in g. So or 10 to the g equals 10,000. So you should have gotten that exponent would be to the 4th. 10 squared is 100, 10 cubed is 1,000, 10 to the 4th is 10,000. So the log base 10 of 10,000 is 4. Now I picked on this one because the log base 10, since our number system is based on tens, that's a special log. So this has the exact same meaning. If there's no number here, if the base is not specified on the log, so if that 10 was gone and it looked like this, it means the exact same thing. So base 10 is implied. when no base is specified. Okay, and your calculator has a log button. So I'll go in here and put in 10. So here's, notice that my calculator program here is interpreting it just like I said. Without the 10 there, I put in log of 10,000, it's telling me the answer is 4. And that's what we said. It's the exponent of 10 that would give 10,000 with a base of 10. Okay, there's another one like this. Look at J. So for J, this is the exponent of E that would give 3. Okay, and they called it, oh sorry, the exponent of E that would, okay, sorry, so 3 is the exponent of E that would give X. 3 is, that's what we're saying, that would give X. Okay, so remember, logs are exponents. So 3 here is the exponent. It's the exponent of E that would give X. So in other words, E to the third power equals X. Now this is a special case too, since we saw that base E is important in terms of continuous compounding, where we worked with continuous compounding. We saw that this base E showed up. So because that's an important base, it also has its own log. So log base E, I can't do a soup. So log base E, say of X, we write as the natural log is the same as the natural log of X. So natural log is exactly the same as log base E. So J could have also been written ln of X equals 3. This statement is equivalent to this statement, just like log of 10,000 is equivalent to log base 10 of 10,000. So whenever you have log base E, the kind of the more compact way to express that is natural log. Natural log is exactly the same as log base E, and we write ln. Now your calculus, so similarly, so let's make up another example here. So suppose we said the log base E of 23. Okay, so if we wanted to write that as an exponent, so what exponent would that be? So first of all, that would be exactly the same as saying ln of 23. This is our shorthand for log base E. So how could we write that as an exponential equation? Well, what is the log base E of 23? It's the exponent of E that would give 23. So we could call it anything we want, call it C. So what are we saying? This is the exponent of E that would give 23. So E to the C equals 23. So there's some, and remember this this number e is 2.71828 dot dot dot. So if I were to put in ln of 23, this is the exponent of e that gives 23. 3.13549 is the exponent of e that gives 23. Now your calculator, it has these two logs built in. The log base 10, which is a button just log, and natural log, which is a button that says ln. So your calculator can directly calculate those two types of logs when the base is 10 and when the base is e. But it can't directly calculate any other with any other base. Like in our example, we saw it was the exponent of 1.45 that would give 793.65. And we said that that was the log base 1.45 of 793.65. The exponent, so this is talking about x. X is the exponent of 1.45 that would give 793.65. And your calculator doesn't have a way of directly calculating any number, any log other than base e and base 10. Those are built into your calculator. But for instance, base 1.45 is not built in to your calculator. So there's what's called the change of base formula. Change of base formula allows us to get a value for this. So in the change of base formula, this log that I've put here above could be written as the log of 793.65. And now without the number there, remember what that implies. So what base is implied by the fact that there's no number there? It'd be 10. Okay, and the change of base formula says we can take this and do the log base 10 of 793.65 and divide it by the log of 1.45. So we just changed the base to 10. So we could find what this log is by changing the base to 10 and taking the log base 10 of 793.65 divided by the log of 1.45. So let's show how that number then equals the 17.97 that we got. And you should try this on your calculator as well to make sure you can do it. There it is. So the log of base 1.45 of 793.65, we can change the base and rewrite it as the fraction, the log base 10 of this number, divided by the log base 10 of the base, the original base. Okay, but the change of base formula allows us to change it to any base. So we could do that same thing with natural log and change to base e. Notice you get the exact same number. So since your calculator can only do base 10 and base e, when you have any other base, you'll need to use the change of base formula to set up a ratio, either base 10 or base e, and it's the ratio of the number that we're taking the log of over, or sorry, the ratio of the log of the number we're taking the original log of divided by the log of the original base. And you can do base 10 or you can do base e, you get the same result. Okay, so a couple of these practice problems that you did, for instance, f is a good one, and d. So when you set it up in the exponential, change it into an exponential form with m or n as the exponent, these weren't ones that you could look at and say, I know what the answer is for m or for n. So it's going to require the change of base formula. So practice with your calculator, see if you can figure out what this value of n is and this value of m is. So pause here, and when you unpause, I can show you and see if you're right. Okay, so hopefully you gave those a shot. So let's see, in order to get the log base 4 of 5, you could choose base 10 or base e. I'll just do base 10. It would be log of 5 divided by log of 4. So what is this? This is the exponent of 4 that gives 5, and so is this. So by using the change of base formula, what I'm finding now is that the exponent of 4 that would give you 5 is 1.16, approximately. Similarly, example D here. Let's use, just to change it up, we'll use natural log this time, because we can change the base to anything we want as long as consistent. So we're going to choose one of the two bases that we have built into our calculator. So this one will be the natural log of 12 divided by the natural log of 7. So what is this number right here? This number is the exponent of 7 that would give 12. In other words, 7 to the 1.277 would equal 12. Okay, so that's an introduction to logarithms. We will have a quiz at the beginning of class Friday after going over the homework. We'll have a quiz over the content of this video. So watch it again if you need to, and you're free to send me an email if you have any questions. Okay, I'll see you Friday in class.